Hi, and welcome to our webinar, Principia, how to combine multi-body simulation with FEA in Onshape for maximum efficiency. Today we will talk about, as I said, finite element analysis in combination with multi-body simulation, and I will do a demo for you and show you how our app works. So first question from my side, please raise your hands if you can hear me clearly. It would be good to know this. Okay, looks good. Thank you so much. So let's proceed. Short agenda for today. I will introduce myself and the company. Then I'll talk about the app in itself, so how it's integrated in Onshape. Then a short theoretical background, let's call it that way. So about what is multi-body dynamics, what is multi-dynamics not. Then I'll show you a demo live in Onshape and Principia, and then we will have some time for questions and answers. All right, so some background to the company. Our company is not too old, so we founded the company this year, and we see ourselves as a solution provider for design validation tools, which are integrated in CAE or CAD platforms. So we do not want to create some CAD software modeling tools. We just want to be an addition to those tools where these tools host platforms. We are experts in designing numerical solvers for modeling dynamical systems, and also to create algorithms or to prove algorithms, to create new things, for example, in the field of inverse dynamics. Then we are experts in UI and UX design. We want to be a leading provider of software that is really easy to use and well integrated in the user's flow, what he does in his, say, CAD platform. And then we, of course, as we are integrating into cloud-native software, we are experts in web development. Myself, so I'm Stefan Oberbersteiner, I'm CEO of the company, and my background in education is about, I did a technical college, so I have experience in CAD modeling. I also did some jobs in the field of mechanical design. Then I did my master's in mechanical engineering at the Upper Austria University of Sciences in Wales. And after this, I joined the research group of multi-body dynamics at the campus Wales. And this time I did my PhD in mechanics at the Technical University in Vienna. My competences are, of course, in the field of engineering and CAD design, and in the field of solid mechanics and simulation tools itself. In the last years, I switched over to software engineering, where I do some method development and software development. Now, before we start with the topic itself, so with Principia, I'd like to start a quick poll, and I'd like to know which industry you work in. So my colleague in the background will start the poll in a second. So I see it, that is already there. So please send me some answers. I also have to give an answer. Okay, there is already some feedback. I have 71% of other. Let's just wait a few seconds. So no agricultural engineers here, and also no production machines. It's just automation and robots and all the other, say, interesting fields. All right. Thank you for your answers. It's always kind of interesting for us because multi-body dynamics itself, so our field is, of course, It has a widespread field of application, and that's why we can, of course, adapt to those fields. All right, so let's start with Principia itself. So what it's all about. We claim ourselves to be the first cloud-native multi-body simulation app. So what you see on the right here in the green box is our app in Onshape. So a bit the bigger picture. So we are integrated as a side panel app into the assembly design environment in Onshape. And with our app, you can create simulation models for dynamical analysis. You not only can create them, of course, you can simulate them and you can post-process them. And the benefit you get, you see it already here in this picture, is with bodies and constraints, we are integrated into the workflow in Onshape. So we take over all the information from Onshape, which is quite a lot during modeling. And then you only have to add some, say, special elements that are needed for a dynamical model. And then you can jump into the simulation and just hit the start button. And it's all from the look and feel quite native, so it's well integrated in the UX concept of Onshape itself. Our app, now we are in version 3. We started to do the same like Onshape does with these 3 weekly updates. We are not at this point right now, but we keep pushing it and we continuously delivering releases. So the first release was released in July, and the V3 now was released in December, a few days ago. The app, as I said, is fully integrated in the Onshape, and it primarily closes the gap between Onshape assembly and finite element analysis. So that's exactly the point we are talking about today. So how can we combine those puzzle elements to make an ideal workflow? And with multi-body dynamics itself, you can compute dynamical loads, forces, torques, interface forces in mate features, so in joining elements, for say any specific interface or any part of the mechanism. Now let's continue with the poll, because I just mentioned the topic multi-body simulation several times. Now I would be interested which methods for design validation you did already know. So the first is finite element method, which is known, I guess, because finite element method is also the topic of today's webinar. So I guess you're familiar with it. Computational fluid dynamics, so like on the picture on the right with some, say, flow of water in a turbine, etc. Then multi-body dynamics and the discrete element method here on the right. This can be seen as the 4 major design validation tools in our field. So please answer the question here. So I'm familiar with all 4 fields of application. Looks like, as my initial guess was, finite elements is something many of you know. Computational fluid dynamics with 25% right now in the poll. It's a bit lower percentage. Multi-body dynamics seems to work, that we spread our word, and that's why I see 31% of you already know this. And the discrete element method is one of the methods that is not too well known. It has a huge potential, especially in combination with multi-body dynamics. So with discrete element method or particle simulation method, you can deal with not only real particles like some soil or underground. You can also deal with showing or modeling fluids as discrete elements. So like you could also exchange the computational fluid dynamics method with discrete element method using the SPH method, and then you can also model or simulate some flows, which can be really beneficial in combination with the multi-body method to account for the interaction between bodies and some flow. All right, so many of you know finite elements and multi-body dynamics. That's good because we will exactly proceed with this topic. So let's start with what is multi-body dynamics. For those of you who do not know, it's all about motion, and it's all about, say, a history of motion over time. And in multi-body dynamics, the primary goal is to study the behavior of interconnected mechanical systems, where the reason for this motion or the behavior is some input, like a force that is given over time, or a spring, which is a force that is dependent on the current state of some bodies. In contrast to that, inverse dynamics would be the case when you already know some output and go back to the reason for the motion. But here in multi-body dynamics, the primary goal is to study the behavior caused by some forces or some other effects. It's all about analyzing forces and interactions between those bodies, and you gain a really you gain insights into the system behavior. So you learn many things about your product itself. You could also use kinematic analysis, which is most of the time integrated in CAD software and also, of course, in Onshape. But with multi-body dynamics, you add some additional dimension, namely the time. So you have some behavior over time, and you can see, are there any collisions? Does the system work like you thought it should work with given forces, with given limits of some, say, hydraulic cylinder, servo motor, etc. You can, of course, evaluate the performance. So you can test with your given actuators of a system, your given drives in a system. Does it really do the job in the time you would like to have it? You can identify issues. So as I said, one issue could be that there are collisions, but all other kind of problems. And you can optimize components and parameters. Optimizing components would mean you can just analyze if there is any interface force, for example, that exceeds some special limit. Could be a screw that connects two bodies, and you have an interface force that is computed via the multi-body simulation method. And then you can say, does this force exceed a special limit given in a table where the screw is defined? You can optimize it in a way that you can choose a larger screw, or you can choose one with a lower weight or with a lower dimension or lower costs. So that's the optimization here. And what is multi-body dynamics not? It is not finite element analysis, because sometimes people mix up things. In finite elements, it's all about a detailed analysis of a structure itself, so the deformation of a structure. And within this structure, in finite elements, you're interested in stresses and strains, so more on the material side. In finite elements, you can also not only deal with this solid mechanics thing, but also some heat transfer or thermoelastic, so coupled behavior between thermal and elastic behavior. And you can also perform some fatigue analysis with finite element results. So given some time-dependent stresses or some load cases, different load cases in finite elements, you can compute how long your part will survive in the real surrounding. Finite element has one thing to do with multi-body dynamics. Exactly the thing we are talking today is finite elements often needs loads. When you do not know any load, finite element analysis or finite element models crave for all these details, and you can generate those loads with multi-body dynamic models. And multi-body dynamics is not computational fluid dynamics, so we are not into any flow of fluids, gases, or liquids. So we only have a finite number of parts that are interconnected, and not many little particles of fluid or anything else. We do not investigate this. Typical tasks of multi-body dynamics are listed here. So we always talk about these three special areas. The first thing is if you want to check your functionality. So multi-body dynamics enables virtual testing and the analysis of mechanical systems. As I said, you can identify issues, or go into detail, look if there are some excessive forces, etc. And if you're able to catch and resolve these issues very early in the development process, using the tool reduces the risk and cost associated with all the physical prototyping. You can do your tests on a virtual site, you can equip your system with many sensors, etc. Then the scaling parts and machine elements topic is all about define your machine elements and your parts or standard parts in our software, and then look if there are some forces exceeding those part limits, because most of the time, if you're using some machine elements or standard parts, you already know those limits. You do not have to go to finite elements. You have some table for roller bearings, for all screws, ball joints, etc. You already know those loads that are the limits, and you can have a look in the time history. Is there any point in time exceeding those forces? And if they are exceeding, you can choose another component. And the last point is the content of today's presentation or webinar. It's a load generation. So if you do not know any load for finite elements, you can create them with multi-body dynamics. So I missed that I already also have some slides here. So for functionality checking, this could be an example here. A two-dimensional motion, and you can check, is there any collision? Is there any collision even if you are exceeding some force or torque limits in the motors? They do not follow exactly the trajectory. You can also go for a collision detection. Then the scaling parts, so I already talked about this, all the tables and limits. And then now I think we can directly jump into the topic. So how we can combine multi-body system dynamics with FEA in Onshape to generate a maximum efficiency by means of a workflow that is closed. So that's exactly the point where I switch to Onshape, to the live demo part. My Onshape window is located. So you now should see the assembly view. Good. So what I've modeled here is a toggle press, so a minimal example consisting out of several bodies. It is well defined in Onshape, so we can move it. So it's a valid kinematic model. So that's always a good check before directly jumping into Principia. You should have a assembly that features only the degrees of freedom that the real system has. So in my case, it's only this 1 degree of freedom of the coupled system. Then what I do prior to opening Principia is I move the system towards the point I'd like to start with. So the initial condition for my simulation. Because when I jump into Principia in the next step, this will be the position that is taken over as the initial condition for the simulation. When I'm done, I open our app with clicking on our icon on the right. Now, Principia loads all the information from the assembly. So all the bodies are modeled in Onshape. I can open them here. I see that there's a mass, so there is a density defined. So when we are able to compute the mass, everything's fine. You can also use our checkboxes here to get some information about some cumulative mass if you are interested in some subsystems. So that's just like the tool in the Onshape assembly itself. Then, as we already defined the kinematics of our model, constraints. So in the multi-body dynamics world, people always talk about constraints. Here in Onshape, you talk about some mate features or mates. Sometimes they're called joints. So here we say these are constraints, so some constraining equations, or constraints that connect bodies with each other. So we exactly use the names that are defined in the tree here in Onshape, and due to the mate selected in Onshape, so fastened, revolute, spherical, we also decide locked degrees of freedom, which are, for some special cases, you can override them and say, no, for this constraint, it is for the dynamical simulation, not a cylindrical joint, but an inline joint due to several reasons. So there are some mate features or mates missing in Onshape. You can create them on your own afterwards here in our application. So this is most of the most difficult part in modeling such a system. So this is all done automatically for you. In other software tools, which can be external, you have to input the bodies, you have to define all the inertia stuff, and you also have to define constraints, which there means create the constraint, do the positioning, do the orientation, etc. So all that's left is define the forces. And in our system, I'd say we have two forces. The main one is I'd like to clamp a part here between this clamp part and the surrounding, or there could be some plate that is located here. So it's just something here against our world environment. So in multi-body dynamics, you probably read this very often when there's world or ground. This means this is something against the surrounding. The surrounding is something that cannot be moved, that is not deformable, etc. So that's the same here. So the tip of this clamp should be connected or connect when with the surrounding when there's contact. If there's some gap in between, nothing to do, no force, only in case of a contact. In Principia, here we can use this bump stop force element. So this is exactly the thing. If there's an open gap, no force. If there's a gap, it's a linear spring damper, which can be defined here. So you only have to select both mate connectors. So it always says action and reaction. In many cases, there's no difference with which element is used. In this case, it is it is good to use the action part, the one that's moving and probably penetrating the other one is the action one. So if I click this pickup button, I can go into Onshape, click on the mate connector, and it's selected for me. Or if I know the name, I can choose it in the drop-down menu and search for it. Then here I have a direction of the force, a stiffness of the force. So this can be probably found in a table as I showed you. So in this case, I really searched for a rubber bump stop, and it said it's in this dimension, it's 120 Newton per millimeter. And a harder one is the coefficient for damping. Sometimes you get it from the manufacturer of such parts, and sometimes you only have to, you have to make a guess. In my case, I had a guess of 1 Newton-second per millimeter. And then the other force that is actually moving the system is the hand force. And I said about 2 kilograms. And with 2 kilograms, I want to get into contact with the surrounding. 20 Newton, so 2 kilograms at 20 Newton. I said it's acting on the hand action point. This is a mate connector I already defined. And it's acting against the world. So as I said, here you see, you can read world. And the orientation is bound to world, which means it's always in the coordinate system you see on the top here. So in X, Y, Z directions of this triad. So I've chosen X, which is the red one. So it always acts into the horizontal direction. And as I said, you can equip your system with any sensor you like. I also added a position sensor, so a displacement one with a mate connector. It says to, and sometimes there's also a from mate connector. So we measure to the clamp tip, which is this mate connector here. And when we are fine with our model, we can, prior to hitting the start button, we have to do some settings like how long should the simulation run? In this case, it's a very quick one. Due to the low inertia, it moves really quick. So that is something that I already prepared. And the other thing here is the gravity setting. So where is the vertical direction by means of the gravity vector? In this case, it's the Z direction. And when I'm done, I hit start. I can go to the history tab where I can monitor the simulation run. So everything runs in the background in the cloud. And when there is 100%, we can click view. An animation that is showing up here. Of course, the time frame is not too long. That's why animation repeats very fast. So let's stop this. And now I'm interested in some force, namely the stiffness, so the stiffness clamp part, which is exactly the contact force. Because I'd like to make a finite element analysis of this blue part, and I don't know what the force is like in the moment of the contact, so when there's an impact, and also afterwards, when the impact is over, you also have some static force here. So that's something I'd like to do here in Onshape. So we can first see everything. So okay, there is a peak load of about 1,000 Newton in magnitude. I know that this force is acting in the perpendicular to this clamp, but I can also write an output of the vector itself. So in global world coordinates, the X, Y, Z forces. But now for the simulation, I'd like to choose the magnitude because I already prepared the finite element or Onshape simulation model for it. So I'd like to just go to the point where there's maximum force. And when I find it, I can hit the left mouse button. And with doing so, we are exporting these values to a variable studio. So this is our interface where data is going back to Onshape. And if you go to the variable studio, you already see the force. So that's the value. And with this value, I can now link the simulation. That's the thing I already prepared. So I do not want to make the full simulation of the entire assembly. I just picked out the parts that are of interest for me. And I already did the constraining. So I have these two bolts here where my part is mounted, or where it is supported. And now I'm only missing the force. That's the thing I do next. So I click on the part I want to load, then the load direction, which is this one here. And now I have some predefined force values. And I know that the force direction here relates, so the X, Y, Z forces are related to the selected mate connector, which is the one here. And the blue direction, the Z direction, is the one where my force acts, because this bump stop force can only act perpendicular to the surface. So I only need to fill this Z force, and now I could just type in the force I just read in Principia, but as I exported the value into a variable studio, I can just link it with using the syntax of Onshape. So I found my value here, and when I hit enter, it's linked. So I can see the value, but if I click into the field, in Onshape, that is already linked to the value. So if there's an update, I'm fine. It will be also updated. The last point here is I want to use the load region. So the force should be distributed over this surface. Now, Onshape simulation runs, and I hope that it will finish soon. So once the simulation is done, I can, of course, post-process something. So I see this force obviously is too high for my part, but I exactly took the peak, which is only acting in a very short period of time. And here one has to say that this very fast deformations are probably not the real thing for this static finite element analysis. But anyway, probably we just want to try it out to now change some or make some change in the geometry to see what's happening. So we switch or jump back to the part studio where this part is designed and want to change something. So I used the parameterization here. I said this is a thickness of 2 millimeters of the sheet metal structure, and now change it to 3 millimeters. So it's thickened. When I jump back, I have to rerun the entire circle, but it's all linked. So you see the updated structure. Then Principia also is updated. In this case, it's not updated automatically. Prior to the automatic detection of the changes, I hit the button. Now, I started the simulation with the new geometry, so everything's new. If it is a problem that is linked to the inertia things, so real dynamical problems where you have the influence of the inertia, everything is included now. So the updates in the geometry, of course, have influence on the mass and the moments of inertia. So we now get some different loads. So the loads are a little bit lower than the one before. I export the values again. Of course, I can check if it's updated in the variable studio, but it will be updated. Yeah, so it's new values. Just go into Onshape again. Finite element solver Onshape simulation is running without any other click. And now I've got the updated values. So you've seen much higher stresses before. This geometry update, now I could think about increasing some radius or etc. So the basic workflow or increasing the efficiency of the design cycles, I think everything's about avoiding copy and paste, leaving your workspace. So here in the workflow, I've just shown you everything is included and it's a closed loop. So that's the point I want to tell you. Using Principia as a load generation tool is not only a one-way direction. It is something coming back from it, and not only the visualization or animation, but also some data. And it will be improved in future. We are thinking about also adding functionality to automatically create the correct configurations of the bodies, etc. Yeah, so that was the live demo. I hope you enjoyed it. I just switch back to my slides quickly. There's something left. So here's the table I just talked about. So it's this bump rubber where I have my stiffness from. So you probably can find this value from many different distributors or manufacturers. All right, and now I hope, as I said, I hope you enjoyed it, and I hope you now have an idea how to use this in your company or in your daily work. The next steps to your trial subscription, if you do not have it right now, is go to the App Store, search for Principia. We are in the category simulation, and then subscribe to the app. We have a free 30-day subscription, and yeah, if you already subscribed, opening the app, I just showed you in the live demo, go into an assembly, hit the Principia button on the right, and you will see our app. All right, so that's all from my side. Thank you so much for attending this webinar. If there are any questions now, I'm happy to answer them. So the question is it possible to do complex MBS FEM coupling simulations because they can be resource extensive? The question. For the second question here, so how many simulations can you run? Is there a limit or tokens that must be repurchased? No, currently not. So in the free subscription, it's fair use. So please do not destroy our infrastructure. I hope you cannot destroy it at all, but no, there is not. And if you are in a paid subscription, there's no limits currently. Then there are two questions. I'm curious about how often your target releases updates regarding the Principia, so we can configure the simulation. For example, keeping the initial thickness for a specific simulation and then adjusting the thickness for another one. So the first question is, I'm curious about how often your target releases updates. I don't know exactly what you mean with this. Regarding the Principia MBS simulation, can we configure the simulation? So you mean changing parameters and then do some variations. So currently you have to make the round trip in Onshape. So everything for the model is defined in Onshape. And then you load this data into the Principia app again and start a simulation. And there you can, of course, have a long history of simulation runs. We also are working with the versioning of Onshape. So you could also try to make branches of your model, and then you have your simulations in these branches. The question below is, can I obtain a text output of the results and post-process myself? Yes, you can, of course. Just show it to you. So let me see. Yes. In the viewer, you have two options. Oh, sorry, it's the wrong model. You can download the animation. This is a very new feature. So the animation can be stored as an MP4 animation for using some presentation. So if you hit this download button here, you will see that there's a download. And for the text file with all the information about, in this case, all the sensors, so not and all the other values. It's not only the plot you currently see, but all the data is stored in this text file. You've seen it here, so it's a comma-separated value file for this for all this data, and the MP4 file if you hit the download button here. Then does Principia support fatigue simulation, how a component fails over a long period of time with wear and tear? No, currently not. This is something, of course, very interesting, and it's the first shoot. In a first shoot, we go into the finite element direction where we say we create loads for some static analysis. Although we know that these are dynamical forces, but this is very common in engineering. And the second step is, of course, going to some transient cases. And here there are several opportunities for especially fatigue analysis, where you can go into an analysis of some, you have some special load cases on your finite element analysis, and you count how often these load cases show up in your dynamical system. This can all be done automatically. This is something we will go into future, but currently we are just into the static analysis thing. So we create loads for static analysis, and coming to those values, especially when there is a different configuration as the one you designed in the Onshape assembly, that's also a big added value to Onshape simulation right now, because there you can only, of course, analyze systems that are well defined without any rigid body motion. So we create the loads for this and not for fatigue analysis right now, even though we are interested in this topic. Good. Any other questions? Okay, so the releases. Yeah, we are of course we want to do it in the same manner as Onshape. As soon as we have some new feature, bug fixes are a completely different topic. We directly push bug fixes or hot fixes into the production stage. But for new features, we keep this interval right now. We did not clearly commit to a 3 or 4 weekly update rate, but we will do. But as soon as there is a new feature, we will push it. Okay. Someone writing? Good. So I hope you enjoyed it, and if there are any further questions, reach out to us. I think you know the channels, so either via LinkedIn, you will find us there, our website, principia-mbs.com, or just try it out, go to the App Store and test our app. Would be great to hear from you. Okay, so thank you once again, and probably we see us next time. We will do webinars in future too with different topics. Yeah, you there. Merry Christmas and a Happy New Year, because we want to do a new webinar this year. It will be next year. So have a nice rest of the week and see you. Bye.